All right. So now we're going to go on to algorithms for multiplying. All right? And so I think I told you already that I had to come up with a new algorithm for multiplying in order to do the compiler. And then I gave it as an exam question, and people did very badly. So then I made up slides, and people still weren't getting it. So we made all those earlier slides. So these are all slides about, well, let's pretend we don't know how to multiply, and let's develop algorithms for multiplying. And in some ways it feels like a lot of slides, but when we did them yesterday, it seemed to go pretty smoothly. And I think, what my goal is in this course is to teach you how to design a new algorithm, right? So we might as well pretend we don't know how to multiply and think about how are we going to design an algorithm for multiplying, right? And it also, another reason for doing this is, haven't looked at it in a while, but sometime over the summer, I was thinking about a high school problem that's not too unlike this, and I did write it up as a potential test question. So it'll probably either be on this coming test or on the exam, right? So what I'm going to state here is let's go through this and make sure everybody could do this. All right? Because this is now we're at the a lot of our examples were really simple, and now I think you should be able to do this in your life. All right? All right. So what is our goal is to multiply, right? And if we're in elementary school, right, we learn the definition of multiplying, and it's you just add y x times. So what's our obvious algorithm? Our algorithm here, everybody sees we're adding x times. So then what is our loop invariant, right? Our loop invariant says, well, what are our variables? Our variables are x and y. We're not going to change. They're going to be our input. We'll keep them so that we know we have them. And we're going to have little variables I and s. And what is the relationship? And here you can kind of say I is the number of iterations, right? So you get every time you iterate, you add y. So s is I times y, right? Everybody good? Really holler if you're not getting this. All right? So that was good, but I want a different loop invariant that isn't. Here, let me tell you what I don't like about this loop invariant. I was saying what I didn't like about it is that I want to do a shrinking the input kind of loop invariant, but I have a bigger complaint, I realize, is that I is so tied to the number of iterations, and I want to be, we want to speed this up, so we're going to be jumping iterations, skipping stuff like we did before, right? So anyway, let's change it. So how are we going to change it? Is we're going to have a value, little x and little y, that's going to start off as our x and a y, and we're going to make them smaller. And so how are we going to initially make them smaller, right? Little x is going to be our measure of progress, right? So what are we going to do? We're going to make little x smaller, and we're going to keep a running sum. We're going to add in y. So in really this algorithm exactly the same as it was before, except little I counting up, we're having little x counting down. Everybody see it's just the same algorithm, right? And so similarly, we can get just the same loop invariant, right? Here, what's the relationship? Little x is going to be capital X minus the number of iterations, right? And y doesn't change, and s is going to be the number of iterations times y, right? So we can do various equations, and we can rearrange, and we get this form. So here I'm just rearranging those equations. All right? Everybody see that? And the reason I like this loop invariant is because it's kind of like what we were doing with the GCD algorithm. Right? We have little x and little y, and more or less they're the answer we're looking for, right? Except we have this extra s in there. Right? Everybody see this loop invariant? Yeah? Nothing. Nothing at all. I'm just turning it around a little bit so I can get a loop invariant I like. Right? In fact, on the test when I gave it to people, I gave them this loop invariant. So all we've done so far is motivated this loop invariant. All right? Everybody good with this loop invariant? It sort of falls naturally from, this is a pretty natural program, and there's the loop invariant. Everybody good? All right. So now let's say all we have is this loop invariant. Right? I don't know where we got it from, but somewhere we got this loop invariant, and let's see if we can develop the algorithm. All right? So how do we establish the condition, the loop invariant? Right? We want to do the minimal work to get the loop invariant through. And remember my motto that the 0 is a really good number, right? So, actually this isn't 0. Here we're setting x to x and y to y, right? I mean, it's the other end of 0. Right? Everybody good? And so, here's our 0. I knew there's a 0 somewhere, right? And so everybody see that we got our loop invariant? Right? We've established it. All right, so now, what's our measure of progress? Well, remember, we have to do two things now. We have to maintain the loop invariant while making progress. And my advice was, well, let's first make progress. And our measure of progress is x, so let's make progress by making x1 smaller. All right? And what is our exit condition going to be? Well, we want the exit condition to be something that's obviously going to be met. Right? We don't make it our post condition. We say, well, x is getting smaller, and it's an integer, so when we exit, when x equals 0. Right? Everybody right? So now, do we get our post condition? Right? Well, from the loop invariant, what do we know? We have the loop invariant. Right? From our exit condition, we have x equals to 0. Right? Well, if x equals to 0, then the loop invariant tells us that s is our answer, right? So we can just, the post condition is to return the answer, so all we do is return s. Right, everybody following? We're all good? All right, so now we need to maintain the loop invariant. So we're going to do the kind of things that we did before. The first thing is we're going to say is what is our measure of progress? Right? We're going to make x1 smaller. So, and remember, everybody remember this picture? We want to say on the path, the loop invariant path, we start by making some progress. That was great, but we fell off the path. Right? Now, it's more clear what we're wanting to do. We keep x fixed because that was our measure of progress. We don't want to backtrack. And now change everything else to get us back on the path. Right? Everybody good with this? So, now, and this is going to help determine the code, because we don't have code yet. Right? So, let's do what we were doing before. How do we get the loop invariant? Right? We say, let the xt be the values at the top of the loop, the yt plus xt plus 1 is the values when we come around. Right? So we can differentiate them. What do we know from these guys? Right? These slides were made first. You'll recognize them. And then I copied them back to the easier example. All right? So you're going to see things you've seen before. I do a lot of cut and pasting. Right? So people are trying, what are people trying to do? They're trying to get the loop invariant here all by themselves. And they're trying to understand the whole algorithm by themselves. and they panic, right? So we don't want to panic. We don't want to do brute force, right? So instead, we do one step at a time. And how does that mean? Is we use the fact that the loop invariant is already true, right? So we're flying in from Mars, and we don't know how we got here, right? We have no idea about what happened before. And all we know is that the loop invariant is true with respect to the old values, right? Everybody got that? And then the exit condition, all right, we haven't exited. And our code, well, this is the math of the part of the code that we have, right? And what don't we have? Well, we don't know, oh, actually, maybe we can fill in some other things. Maybe we know that we're not going to change our y, right? And what's our s? We don't know, right? So now we're going to do right side, left side, and see what happens. We're going to say, well, what we want to prove is that this, we got to get our loop invariant. For the new values, we have to prove that this equals this, right? So we write that down, and then we use the stuff that's up there, right? The one thing we use, right, to bring things together. We use what we have to bring them together. We know the loop invariant, which brings us to here, right? We know the plug in the new values. Well, here's the relationship between the old values and the new values, right? And then we see this funny math here. We don't like that. So we multiply through. Right? Everybody with me? All right, now we just got this equal sign left to deal with. Right? We got to here, we got to here. Now how do we deal with that? And we kind of say, what do we need for our equal sign? Well, this has to equal this plus this. Right? Everybody see that? It just falls out of the proof. Everybody doing this? We're all good? You guys are awfully dead looking. Right? I don't like dead people. Right? So here we get our relationship. Right? And now we have a proof. Right? This proves that we maintain the loop invariant. Right? Everybody got that? Yeah? This step here? Well, I didn't have this part of the code, right? So I didn't know what this is. And then I had to make this an equal sign. So how do we make it an equal sign? Well, this clearly cancels with that. And all we have is that this equals this plus this, right? And that gives us, what's this need to be? This needs to be this plus this, right? Does that make sense? So now that is a perfect answer for a test question, yeah? Okay, which parts? The whole thing? Yeah. Yeah. All right, so our loop invariant is this, and these are our original inputs, right? We're not going to change them, so we always can talk about them. What do we have? We have three variables as we go along, little x, y, and s, and they have this has to be true. The code is going to have three variables, little x, little y, and little s.
No, I know, but where does lower x start at?
Well, right now, it's none of your business where it starts, right? Right now, all we're saying is we have these values, and this is true, and we need to maintain it. Now, if you want to go back to an old page and say, how do we establish the loop invariant, right? then I'll tell you the way we establish it is we set little x to capital X, little y to capital Y, and little s to 0. Right? That's how we establish the loop invariant. Where this relationship came from? Well, we did that first program where every iteration we added on y, and we had to count how many iterations we did. And so the one method was to count I increasing from 0 to capital X, right? And then we looked at a new, and I mean, in this case, I would give you the loop invariant, so you just have to trust it, right? So, but how did I come up with this loop invariant? I said to myself, what kind of code do I want to be looking at, right? I wanted to have, this seemed like the obvious algorithm, right? So I'm jumping in the middle of the algorithm, middle of the computation, and I want to say what's going to be true, right? And I don't know, I came up with this to be true, right? And why did I come up with this to be true? Well, maybe I had good intuition, or maybe I wanted it to look more like I have some smaller numbers and the answer is similar, right? Or maybe I looked at this kind of code and said, well, this basic code, what am I maintaining, right? And I kind of banged out and thought about what's true for this basic code, and I got this, right? But now, I mean, you can bang out and see that this is, that this is the relationship. Yeah. Yeah. We haven't gotten there yet. No, we haven't gotten there at all. We're still in kindergarten. All right? So what's the big picture of what we've did is I laid down the kindergarten algorithm, and then I compared if I is the number of iterations, then little x is going to be capital X minus the number of iterations, right? And if I keep adding on y, then s is going to be the number of iterations times y, right? And then I rearranged these, and I got this, right? That's it. I took these, I rearranged them, and I got this. And why do I like this form? It's because this is kind of my precondition. This is my input, and these are the variables that I'm working with. And it tells me that it's a nice loop invariant, that the variables that I'm changing are going to all, it's kind of like conservation of energy, right? My location and speed and direction are all going to change. But there's some equation, which is potential energy plus kinetic energy, which is going to be a constant, right? So here I kind of put it in the same form. I want to be able to play with my x and my y and my s, and I can play with them however I want, as long as I maintain this invariant, right? And another thing why I like this invariant is because I want invariants to when they start off, they really look like the precondition. And then I want them to flow reasonably nicely, and then I want them to look like the postcondition, right? And does this, well, if you set x and y to be x and y, and this to be 0, we have the precondition, right? Without doing any work whatsoever, we have this true, right? And how do we get the postcondition? Well, if our measure of progress is x getting smaller, then when x is 0, we have our answer, right? So now I hope that you can at least trust that this is a reasonable loop invariant, right? Everybody kind of buy that? So, but the other way we could be doing this, if this was a test, right, then I would give you the loop invariant, and you would just have to go in blind faith that I knew what I was doing, right? So this part was how did I come up with the loop invariant? And now we're switching over to I've told you the loop invariant. Now I want you to come up with an algorithm and prove that it works. All right? So imagine you arrive in here, you know nothing at all, we're all writing a test, right? And I tell you that the precondition is x and y, and the postcondition is their product, and the loop invariant is this, right? That's the question. It's at the top of the question. That's all you have, right? And if that's all you have, now your job is to come up with an algorithm, right? And what I've always kind of believed is that if you have the algorithm, then if you have the loop invariant, then the algorithm should sort of fall out naturally, right? And so let's see if that's true, right? Everybody good? So what's the first step? One step is how do I establish the loop invariant, right? And that's that, right? The next step is, well, what's my measure of progress? And actually, in this case, I would probably tell you that x is our measure of progress, right? Probably tell you that. And then how do you get the postcondition? Right, we did that, right? Now, how do we get the code? Right? So, right? So we write the code down, right? So how do you get the code? Is you say, well, let's first put down the relationship of making progress in one iteration, and well, let's decide that we're not going to change our y, and now let's see what we need to do for s, right? And we start writing down the proof of maintaining the loop invariant, right? Because you don't know what code should be, right? And instead of panicking, you leave the code blank and you go down to doing parts that you can do. Can I establish the loop invariant? Yeah. Can I get the postcondition from the loop invariant? Yeah. Do I know what my measure of progress is? Yeah, it's coming down, right? All right, so let's stick in here. We got our measure of progress. It's coming down, right? All right, so now the next thing you can do is say, well, let's try to prove that we can maintain the loop invariant. And how do you prove it? Well, the way you prove it, what I want to see on your paper is you first write this. Everybody got this memorized? Right? Then you write this, right, which talks about the values, the old values and the new values, right? And then you write this, and then you write, what do I know from the loop invariant? I know that, then you copy down, right? You go back to my question, right at the very top. I tell you what the loop invariant is, right? So we're doing no thinking whatsoever yet, right? All we're trying to get this whole algorithm with doing minimal thinking, right? Because as soon as you have to think, problems happen, right? So you take the loop invariant and you copy it down here, except you say it's true for the new values, right? Here, do we know the exit condition? Well, in this case, we figured out our whole exit condition thing, measure of progress thing, right? What's our code? And here we want to put the relationship between the old values and the new values, right? So here we put everything we know so far, right? And we got a question mark here, right, that we're going to fill in. And so then we start proving, right? We need to prove what, then you got that already, then start at this end, right? Don't start waving your hands in the middle until you got this on one end of your page and you have this somewhere else with a little space in the middle that you can wave your hands, right? So we started here and we worked this way, and then we started here and we worked this way, right? So working this way, we say, what do we need to be true for the loop invariant? Well, you go back up to what I told you at the top of the test, and you copy it down here with respect to the new values, right? And if it feels like they're numbers that need to be equals, then it's nice to have equals, equals, equals to make it true, right? So here I'm saying, what do we need? We need this to equal this, right? That's our new loop invariant. Now, how do we get it? Well, we need to go this direction equals we need to go this direction and see if we can match them up, right? Just banging at it. So you see, what can we apply? Oh, look it. I know this is true, so let's use it, right? What about this direction, right? Here's all the new values, and this is new values. No, this is new values, this is old values. You got to translate, right? So let's take the old values and translate them into new values using this stuff, right? And then what's remaining, and then we rearrange. What's remaining is this equals. And how do you get this equals? That's where we need to say, oh, I got to make this equal. I want this proof to work. So we're fudging, we're changing the world to make the proof work. And how do you make it work? You say, well, what do I need this? What I don't know? I don't know this. So what does this have to be? This has to be this plus this. Right? And you write it down. And then, bang, we wrote it down. And now now you've finished the hardest part of the test. Right? Yeah? Yeah. That's what we're doing. Loop invariant t to loop invariant t plus 1. Yeah. What? Yt here? What? Here? That's not part of the loop invariant. That's part of the code. But yeah, because at some point I decided I'm not going to change my y, right? And we could have had this be a question mark, and then you could have said, oh, how should my old y, my new y relate to my old y? And you say, oh, I could make them be equal, right? We could have, right? Yeah. Right? Well, if it's obvious to you, then even better. No, but we didn't have the code yet, right? I told you, so what we were doing there is we were pretending that we didn't know the code. We were pretending all we knew is that I told you the loop invariant, right? So from here to here? Well, I just subbed in the values. Xt plus 1 is xt minus 1. I subbed that in. And y's didn't change. And the new value of s, I don't know. Right? Which is kind of what I'm solving for in order to get my code. From the second to the, from here to here? Here to here? No, here to here is these two. I rearranged y times x minus y times, all right, y times x plus y times -1. Right? I needed to get it, I wanted these to look similar, right? I'm reworking it to try to get this to look like this, right? You got to play with it some. Maybe that was the creative part, was how do I rearrange them to make these two things look the same, right? Yeah. Yeah. Well, now we need code. Yes. Yes, because here, I want here is the relationship. I said code B, but I don't want code B. I could go through all my slides and change it, but I'm lazy. What do we want here? We want the relationship between the old values and the new values that the code gives us, right? That's what we want here, right? And to the extent that it's the same as the code, we're fine. But to the extent that they're different, you got to clarify how they're different, right? So, and here, when we're maintaining the loop invariant, we have old values and new values. So you kind of need that, right? If we're establishing the loop invariant, right? If we're doing pre-code to loop invariant, the loop invariant only appears once, right? And maybe every value only has one value. Every variable has one value, right? So you could just write the code here. That might be okay, right? Well, you want a proof that follows, right? Here, this needs to be the loop invariant stated in terms of the new values. This has to be in terms of the old values. You have to get from here to here. And what gets you from here to here is the relationship between the values. And that's math, not code. Right? Any other questions for this? Yeah. Right. Yeah. Yeah. Here? This just says the y isn't changing. The new value of y equals the old value of y because we don't change it. Versus the new value of x is one smaller than the old value of x. Right? The new value of s is y bigger than the old value of s. Why is s increasing? Well, if you want to make this stay constant, if this comes down, something else has got to go up. Right? So how do we make this constant? This comes down by 1, and this goes, this is going to stay constant. This is going to stay constant. X is going to come down by 1. S is going to go up by y. Yeah. Yeah. In fact, I got proof by pictures over here. All right? So maybe this will help again. Proof by, I love pictures. So here's the loop invariant by pictures. Everybody see it? The area is capital X times capital Y. Here the area is the little x times the little y. And here's the area of S. I'm saying that this area equals that area. Right? Yeah? Because this is a product and S is a number by itself. This area equals this area. I'm just trying to get what this says. This is a square, this is a square, this is an area. Right? So what do? We make x one smaller. right? We're cutting that off. And what's the area we're cutting off? Right? The area we're cutting off has area y. Right? So this becomes, and so we do that, and now we have our loop invariant again. Right? Here's our old values. Here's our new values. Proof by picture. Everybody see that? If you drew these pictures, I as the marker would be pretty happy. Right? Everybody following this? Oops. Right, so there's our code, right? And then we had to translate it, the math, back into code, right? We'd say we're not changing y, x is getting 1 smaller, s is getting y bigger. There's our code. We developed our code. Right? Everybody good? All right, but we just developed elementary school code, so that's not very exciting. So what's the running time? It's order x, which is that linear time, right? We review this and we say, no, the number of digits is log x, so the running time of this is exponential. Right? Everybody good? Right? So now we got to say that's not a good algorithm. Right? I told you if you have inputs of value, you better not subtract 1 every iteration. Right? You have to make it much smaller. You have to divide by 2. All right? So we're going to develop a new algorithm. All right? In which we divide by 2. All right? So we're going to start all over again. Now, do we have to change how do you establish the loop invariant or how you get the postcondition? We're not changing that, right? We're just changing this part. In fact, so here I'm saying I fly in from Mars. I don't know how I got here. Well, what's good about that is I don't know if I got here by subtracting 1 from x or by dividing x by 2. It doesn't matter to me how I got here. Right? All I know is I'm here, and my loop invariant's true, and I need to maintain it. All right? So let's do everything we did before, except we're going to make faster progress. Right? So we have our loop invariant for the old values. We have our exit condition. We have the relationship between our old x and our new x. Right? And what about our new y and our new s? I don't know, right? I don't know what they're going to be. So what's my new loop invariant going to be? Well, we start doing it. Everybody good here? And we need this to be equal. So we start doing exactly what we were doing. We use the loop invariant. We get that, right? We know it's true about the old values. We plug in the new values. Right? What's the relationship between the new value of x and the old value of x? We plug that in here, right? And here we don't know what those are. Question marks. Right? Everybody here? So then now we have to do the magic in here. Right? We have to make this look like this. And we have to do it we can make this to be whatever we want. We can make this to be whatever we want, and we got to make this equal this, right? Here, x is coming down by a factor of 2. So, come on, everybody look at that. What do you want your y and your s to be? Right? What are we going to do? Multiply y by 2, right? That's pretty nice. X comes down by 2, y goes up by 2, right? Then, what do we need s to be? S doesn't change. Right? Everybody good? So, there, we have our proof. Right? Let's do the same, proof by pictures. We have this. We cut the x in half. We rearrange. We put them back together. Right? Everybody see that? Yep. Well, before we subtracted 1 from here, and then to bring it back up again, we added y to s. And now x is coming down by a factor of 2, and y is going up by a factor of 2. Because we need to maintain the loop invariant, and we need to do it faster. Right? We need to make progress by dividing x by 2 so that our algorithm has good running time. Right? Otherwise, it's exponential. If you subtract 1, it's exponential in the number of bits. Right? If you divide by 2, it's linear in the number of bits. Yeah? All right. People are kind of wondering about S now. Right? Any thoughts about, are there any bugs in what I'm doing here? What if it's not even? Right? This is a great algorithm, right? But is this a real number? No. I want these to be integers. So if they're integers, when I divide by 2, it's divided by 2 round down, right? So this only works when x is even, right? So that was good. And now we have to think, what do we do now, right? So one option is we could change this so it's kind of x minus 1 divided by 2, right? That's the round down. Everybody good with that? If x is odd, then one way is you subtract 1 and divide by 2, right? And then we could go through all this math again, and we could get the even step. I mean the step when it's odd, right? Everybody follow that? Right? Well, what we could do is we could start all over, and we could say, instead of saying, right, before we said xt plus 1 is xt divided by 2, right? And we worked out what we needed to do. But now, really, we're going to get this. The new value of x is going to be the old value minus 1 divided by 2. Right? Yeah? Yeah, only if it's odd. If it's even, we do what we did before. If it's odd, you don't believe me here, I tried 7. Right? 7 divided by 2 is what? It's 3. Right? How did I get that? I subtracted off 1 and I divided by 2. Right? Yeah? Yeah. And in fact, what I would have done, because I'm a casual, wave my hands kind of guy, is I assume everything is the way I want them to be, right, in my first pass, right? In my first pass, we did what we did, and we say, oh, that was really nice. Does it work? Oops. It only works when x is even, right? But it gave me a real good idea of what needed to go on, right? And then we can go back and we say, okay, now we could do it again for this, right? Yeah? Yeah, you have to ask, is it even, is it odd? In my pseudocode, I think I'll actually say, is x even or is x odd? Right? Everybody good? Now, do you want to do this? It feels hard, right? It feels ugly. I don't like ugly things, right? So let's think about what we could do instead, right? We know how to maintain. We have 2 algorithms so far to maintaining the loop invariant, right? If x is even, we divide by 2. Now, what was our other algorithm? Subtract 1. Right? Yeah, so let's just do that. Let's just keep going and say, well, what's our algorithm here? Well, right, here's our algorithm. Oops. Right? You divide x by 2, you multiply y by 2. Right? But can you do that? You only can do if they're even. Right? So what do you do if they're not even? Well, we had that other algorithm. That other algorithm is pretty good. It subtracts 1 from x and adds y to s. Right? Now, is this going to maintain our loop invariant? It'll maintain our loop invariant. Why? Because I dive in from Mars. I know the loop invariant's true. I don't know why it's true. Right? I don't know if it's true because you've been dividing by x or because you've been subtracting 1. I don't care why it's true. Right? All I know is it's true. And if x is even, I know I maintain it. And if x is odd, I know I maintain it. Right? So is this a good algorithm? Yes, it's a good algorithm. Now let's talk about our running time. Right? How much progress are we making? Well, here we're doing great. Here we're doing lousy. Right? But what do you know? Every other iteration, you're dividing by 2. Right? Right? It's like what we did before. Do I know I make progress always? No. But I know that I'm not going to do this twice in a row. Right? Because if it's odd, then the next iteration will be even. So I'm not going to do this twice in a row. So every other iteration, I'm coming down by a factor of 2. Right? And so this is what we call, remember we had that magic trick with the cards? That same magic book had an Ethiopian algorithm for multiplying. I don't know why it was in a magic book, but there it was. And I said, hey, that's a cool algorithm. And this is what the Ethiopian algorithm was. You have beans, and you keep dividing the x and multiplying the y, and whenever, right? So that's the algorithm. You have a pile of x and a pile of y. If x is odd, right, then you have to add y, the current value of y, to your other pile, right? Right. People kind of following this? All right. Now, before we go on to something scarier, I have some slide at the very end which talks about that last algorithm. You might say that last algorithm is really weird. And let me prove to you that, or hand wave, this is a proof, right, that the algorithm we just did is the high school algorithm. All right? Let's see. Here's our algorithm. I'm going to prove to you that this is what you do in high school. All right? So we're going to do this in binary, but it's really all the same. All right? The only difference between you multiply by 2, you multiply by 10. Right? So let's write down some number. Let's call that y. Let's write down some other number. Let's call that x. And my goal is to multiply them. Right? How do I do it in high school? I take this digit, I multiply it by that, and I get 0. And in fact, let's change it so that you know what we're doing the first time, right? I take this, I multiply it by this, and I get that, right? And what is this? That's y, right? And then, and note, I test. Is x even or odd? Right? And if x is odd, then I'm adding in the current value of y. Right? So this, what is this? This is the current value of y. I'm putting in my list, I'm adding it in. Right? And then what do? I divide x by 2. Right? When I divide x by 2, that gets rid of this. Right? Everybody see that? And then I check to see if it's even or odd. In this case, it's even, so I don't multiply the current add in the current value of y, right? But y does get multiplied by 2, right? And then I divide by 2 and I look at this. All right, so here, what would y multiplied by 2 is this, right? I just shift it. It's 2, it's bits, right? It's like multiplying by 10, right? But we're not adding that one in. So then I multiply y again, right? Here y is 1, 0, 0, 1, and it's odd. So do I add it in? Yes, I add it in. Right? People following this? And then I add this up. And what's the sum? The sum is S, right? S is our running sum. Does that make sense? So it's not such a weird algorithm.